The rest of the course is going to be about a new theme. Okay, it's going to be about like how to handle uncertainty. That is, you don't know the future or you don't know something. How to still design algorithm for that. Okay. In the past, we have seen at least like maybe dynamic graph algorithms. So it's kind of handle uncertainty as well, right? Like you have some inputs, but now the input change, and you need to kind of update your output accordingly. So that's one aspect of how to handle uncertainty. But this part is going to be like a kind of new aspect, okay? And it's called competitive analysis of online algorithm. So today is just going to be about this concept. And then on Thursday, we will see how to use LP, like a primal dual method that we have seen, to apply to this kind of new scenario. Yeah. But okay, as a warm-up, let's look at one really simple problem that actually capture a lot of scenario that you will need to face anyway. It's called ski rental problem. It's a fundamental, most basic problem in this area. So what is this problem? So basically, you suppose that you are on vacation, and you're gonna go to play ski, yeah? And you need to design on each day whether you wanna rent the equipment. Let's say you pay $1 per day. Otherwise, you can choose to buy the equipment, and it's like $B. But once you buy it, then you don't need to ever pay again on the next day. If you rent it, then on the next day you rent again. Okay? So that's the scenario. On each day, you need to design whether you want to rent or to buy. However, what you don't know is this. You don't know how many days you have for your vacation. Like, there's going to be some day that your boss said that, okay, come back to work. And now you need to end your vacation. So if you just buy your equipment, and then on the next day your boss say, okay, come back, that's not good. Okay. So what to do, right? What's a good way to deal with this? And this is something that you can imagine, like it's about renting anything, whether you wanna buy some server or you wanna rent the cloud computation, something like that. Okay. Okay. So is the problem clear? Okay. So let me ask you first. Suppose that you forget about uncertainty, right? Suppose that you know the future. That is, you know when the boss will end the vacation. Suppose you know this exactly. What would be the optimal cost? Yeah.
Would be, I guess, min of B and then number of days.
Okay. You said that it's going to be the optimal cost. Yeah. The optimal cost is just going to be the minimum between the number of days and B, right? Why? Because if there are less than B number of days, you know that, then you just keep renting. Just pay the number of days. But if you know that there are more than B days anyway, just buy the equipment from day one. So that's the optimal cost, if you know the future. Okay. But yeah, the key question is, what if you don't know it? Do you have any suggestion on the strategy so that you can pay, let's say, at most 2 times optimal cost when you know the future? Yeah. Any suggestion? David?
I guess you could like rent one per day until you reach B days and just buy it.
Very good. Yeah, exactly. So you said that how about just try to rent for B days and then buy it after that. Yeah. So exactly, that's the like nice and simple algorithm. Rent for B days and then buy. So let's try to analyze this, right? So suppose, like, we don't know this, but suppose that the number of days is less than B. If that is the case, then you know that the optimal cost in this case is number of days. In this case, the online cost, the cost that we pay, is just the number of days as well. So in this case, actually we basically as good as optimal solution. But on the other hand, if the number of days is more than B, right? Here you know that the optimal cost is B. But how much we gonna pay? Still like at most 2B. Because we rent for B days and then buy. So that's 2B. So compared to opt, this is 2opt. So in either case, although we don't know what will happen, we never pay more than 2opt. Okay. And when we know that we are competitive to the algorithm that even know the future by a factor of 2, then we say that the algorithm is too competitive. So this is like the idea of competitive analysis. Okay. So let me try to formalize the whole setting. Yeah. Like there can be many problems in this kind of way, and the setting is like this. In online algorithm, the setting is that there's gonna be online sequence of events. Yeah. So like even the first event, E1, E2, E3, and so on. And we don't like it revealed to us one by one in the online fashion. So we don't know what is the next event. Yeah. We don't know the length of this sequence too. Yeah. So the algorithm will need to, on each time step I, we need to make some choice. And the thing is that whatever you make, like once you make the choice, you cannot revoke it. It's irrevocable. Okay. Once you make something, the choice, then you cannot go in the past and change it. Okay. And to measure the quality of online algorithm in general is to use what we call competitive analysis, which is you compare the quality of your algorithm, the online one, even with the optimal offline algorithm. By offline, I mean the one that knows the future. Okay. So it's like a really strong guarantee, but you see that like just previously, we can sometimes like guarantee this kind of strong guarantee. Okay. So this is the idea. Okay. Compare yourself to even the best algorithm that know everything. Yeah. Okay. So more formally, let's say that I use opt of the sequence to denote like the offline optimal cost. Yeah. That is the one where like the whole sequence is known, it's not the future. That's opt of sigma. And we say that the algorithm A is alpha competitive. Yeah. The alpha competitive algorithm A is an online algorithm that for any sequence that we don't actually know, like that is kind of revealed to A one by one. The cost of A is just almost as good as opt up to alpha factor. So you see the similarity to opt, like approximation algorithm. Yeah. But like here is like, it's about like, we try to be as good as opt up to alpha factor. In the approximation algorithm, both algorithms like have the same kind of knowledge. But here, the optimal solution have full knowledge. We have limited knowledge, but we still want to be as good as opt. Okay. We can also talk about randomized algorithm. The algorithm A here can be randomized, and if it's randomized, then we can talk about the expected cost naturally. And basically what we want, right? We want this alpha is called competitive ratio. And we want this competitive ratio alpha to be as close as 1, to be as good as opt. Okay. So that's the setting. And in this online algorithm, there is I need to tell you another concept which is called adversary. So basically what is adversary? It's just the guy who generates the input sequence, the guy who generated this thing. That kind of, and this guy, this adversary have two types. One is adaptive and one is oblivious. So what do I mean? Adaptive adversary is the one that chooses the next event adaptively. Like the next event can based on the previous output of the algorithm. Okay. Think like the user or your boss, he knows when you buy something, then he can generate like whether he wanna end the vacation or not. Okay. Or next is oblivious adversary. So this is the one that do not see the outputs of the algorithm. It just kind of generate this whole sequence obliviously. Like it doesn't concern what the output of the algorithm is. But we still gonna assume that it kind of know the source code of the algorithm. So it doesn't see the output, but it knows the source code. You see more like why you know this a bit more by the end of this lecture. Okay. But for now, just think like it doesn't really adapt the sequence according to the output. Okay. And clearly, like adaptive adversary is kind of stronger. It's harder to work against it. If you want to design algorithm with small competitive ratio, it's going to be harder to get small competitive ratio against adaptive adversary. It's just stronger. So the theme again is this. Everything you have seen so far in the course is kind of offline algorithm, except dynamic algorithm. Like in offline algorithm, basically you know everything. The input is given to you. The whole input is given to you all at once, and you just make the decision based on the entire input, and you want like optimal solution. But for online algorithm, it's kind of limited knowledge, and the input is sequential, given to you one by one. You need to design something now incrementally, and it's irrevocable. Okay. And you want competitive solution, maybe not optimal one. Okay. So any question about the setting? Okay, so let's come back to ski rental. Can we hope for better than 2 competitiveness? Okay. What do you think? So the answer is actually not clear. You can my answer yes and my answer no. There are 2 correct answers. So let me try to tell you that it's basically no. You cannot do better than 2 first, and then you see why you can do better than 2 too. Okay, I don't want to confuse you. Okay. So suppose, right, think of yourself as the boss. You are adaptive adversary who want to make your employee like as sad, as miserable as possible. Okay. What would you do? Okay. What would you, when should you end the vacation? Yeah, Scott?
You wait for them to buy B and then immediately end the vacation, right?
Exactly. Yeah, that's the way to make it like as wasteful as possible, right? Like you just bought it, then let's come to work. Yeah, that's the. So if you buy it on day K, then end with the vacation on day K. And if that is the case, then the competitive ratio is going to be what? So the cost, the online cost is then what?
K plus B.
K plus B, yeah. K minus 1, yeah,
Minus 1.
plus B. Yeah. This is the number of days to rent and then buy. But the op is going to be,
Mean of those two.
yeah, mean of K and B. Okay. So if you look at the ratio here, this ratio, is basically 2 minus 1 over B. Right? Maybe ignore minus 1, then you consider it's at least 2 because the above is like the sum and what below is like minimum of the 2. So this is at least 2. But then because you have this minus 1, then you get like 1 minus 1 over B here. But basically when B is big, then this is basically 2. Okay. So when your adversary is adaptive, you cannot actually get anything much better than 2 when B is big. Okay. That's the point. And an adaptive adversary can actually force the competitive ratio to be basically 2. Okay. But now what if the adversary is oblivious? So let's now consider a new algorithm. It's a quite simple algorithm too. And the algorithm is here. Let's say I toss a coin from the beginning. If it's head, then I'm just going to do the same strategy. I'm going to rent for B days and then buy. But otherwise, if I get tail, then I'm going to rent for like a 3/4 B days and then buy. Okay. So let's try to analyze this. The cost of this algorithm. Okay. Oh. Okay. So suppose that I use let T be the number of days. Okay, there's going to be 3 cases. If suppose that the T is less than, there are not too many days. Okay. In this case, an online cost or the algorithm cost is what? It's just T and the opt cost is t as well, right? There's no, so here like it's kind of good case. Next, if t is actually between b and 3/4 b, okay. In this case, what is opt? Yeah.
Still T.
Still t. Yeah. They are less than b days, so the best way is just to rent. Okay, but now this is non-trivial. What's the expected cost of the algorithm? So there's one half chance that this happen, right? If the first thing happened, then what's the cost here? T. Yeah. And then another chance is what's this gonna be?
B.
It's gonna rent for t day and then buy.
Isn't it rent for 3B over 4 days and then buy?
Yeah, but now like the number of days is more than like, okay, maybe I do this, yeah, just to make it clear. Yeah. Okay. Maybe like this. Good. Then it's gonna be t. Maybe basically it's gonna be
3B
like
over 4.
3b over 4 and then plus b. Agree? Okay. Okay. But note that now let's try to analyze this, right? Well, what is b compared to opt? Like t is just opt, right? What is b compared to opt? We know this thing. So b is at most basically b is less than t, which is opt. So now we can try to like write this thing in terms of opt. Okay. So basically it's like opt of what? Like 1/2 plus okay, 1/2 times, this is at most, yeah, so this is 1 plus 4/3. Agree? Yeah.
Should it be a less than instead of an equal?
Yeah, that's that. Yeah.
This is their second event they want to do, and they're offering for 5 and stuff.
Okay. So good. So what's this? Like yeah. This is like basically 7/3. It's like average of 1 and 7/3, which is what?
7 or 6.
So
Or 6.
I think I have it in my notes. So yeah, 10/6, something. Yeah, but it's better than 2. Better than 2 opt. Okay, good. So that's the second case. What about the third case? Is when t is more than b. Okay. So here opt is b. What's the expected cost of the algorithm? Well, let's look at the first case. If this is the case, then we're gonna do what? We're gonna do like before, where like we just rent for B days and then buy. Yeah. If you just do this, you're gonna pay like a 2B, which is 2 opt. But there is another case too, which is 1/2 plus rent for this many days and then buy. This case is when you do better than 2 opt. Okay. So one case is like basically 2 opt. Another case is better than 2 opt. You do the average of the two. So it's gonna be better than 2. Okay. And this is this thing. I calculate for you, but yeah. So this is basically something like 1.8 something. This is also better than also less than 1.8 something. So you see this is strictly better than 2, no matter what B is. Yeah.
Is 3/4 the optimal cutoff, or?
No, there are better trade-off, and you're gonna see the best way next class. Yeah. I just choose 3/4 because it's the easiest to write, I guess. Yeah. Okay. So okay, this is the analysis, and yeah, you get something strictly better than 2. Okay. So what's going on? Once it's against adaptive adversary, you know that you cannot do better than 2. But here we do something better than 2. So it means that we need to actually exploit that the adversary is oblivious somewhere. Where did we use this? Yeah.
So when we're looking at the expectation, it assumes that the adversary doesn't know which option we picked. But if this was an adaptive adversary, then it would be like the max of these two, because it could pick which scenario it wants.
Exactly. Very good. Yeah. Basically, once we say that there is like 1/2 chance that something happen, another half chance that another thing happen. This is true because our like a random coin here is independent from the choice of the adversary. That is like we just assume that the adversary doesn't know our random choice here, right? That's why like this 1/2 and 1/2 here makes sense. If not, then it just doesn't make sense, this analysis. So we really exploit that the adversary is oblivious here. Okay. So the answer is basically here. If adversary is adaptive, then 2 is the right answer. If it's oblivious, then actually we get something better than 2. And next class, you're gonna see like a best way, the optimal way actually, to get something better. And it's gonna use LP, like online primordial way. Okay. Good. Questions? All right. So this algorithm is randomized. So I claim that actually any deterministic algorithm must have competitive ratio, cannot have competitive ratio less than 2. Okay. Why is that? Why do you think so? Like even if the adversary is oblivious, it's still gonna I said that even oblivious adversary still know the source code.
Because if the algorithm's deterministic, then knowing the source code is the same as what the adaptive adversary knows. Because if you know the deterministic algorithm, you'll know what they what step they take at every input. So there has to be some randomness so that knowing the source code isn't enough to know the output.
Very good, very good. So let me explain. Yeah. Like just in the case of ski rental setting, right? Ski rental problem, like the adversary will know the source code even if it's oblivious. And if the algorithm is deterministic, basically once you know the source code, you know everything. You know everything that will happen, that every decision that this deterministic algorithm will design. Because you, as an adversary, you can generate the input to the algorithm, and basically everything is determined. So you would know, the adversary would know the buy day, the day that you're gonna buy. And then it could just apply the same, it could apply the same adversary strategy like before. Although like it can be kind of adaptive according to the source code. Okay. So the point is that when the algorithm is deterministic, oblivious adversary is basically as strong as adaptive adversary. So we can exploit oblivious adversary only when you are randomized, and then we exploit that the adversary is kind of oblivious to our random choice. Yeah. So by oblivious here is oblivious to our random choice, but not to our source code. Okay. So another way to put the state of the art is then here. That is, any deterministic algorithm cannot, is like the best is 2. The best competitive ratio for deterministic algorithm is 2. And randomized one is just better. And in this area of competitive analysis, we're gonna always assume that randomized algorithm assume this oblivious adversary. Okay. Good. So let's see more example. In this case, it's just online scheduling problem, a simple problem where you have, let's say you have M machines, like machine 1, yeah, M machine, M1, machine. It's like a bin, and then there are online sequence of jobs. Job J has size Pj, so maybe like maybe I have, let's say, just 3 machines. And then job J has like this size, P1. Then the next job P2 come in. The next job P3 come in. And then the next job P4, maybe of this size. So when a job comes, you need to design where to assign this job to which machine. Yeah. So, okay. So we don't know n. There are n jobs, but we actually don't know n, the number of jobs. Like the task is that you need to assign each job to one machine. And the goal is and the load of the machine is just a total size assigned of the job assigned to it. So the load of this machine is like this much. The load of this machine is this much. And we basically want to minimize the maximum load. Is the problem clear?
Yeah.
Good. What would be the simplest supernatural way to solve this problem?
Just assign the job to the machine with the that currently has the smallest load.
Yeah, like just be greedy. Given a new job, just assign it to the least loaded machine. Sounds like a good idea, but we want to analyze it, right? We want to say that it's actually competitive. So how do we do it? Okay. So what I'm going to do is I'm going to define the average load. Okay. The average load is just basically the total size of all jobs and averaged by M, the number of machines. So if somehow we can really average the total size to all machines, this is A. Okay. And then next is the maximum job, which is max overall, like job and the size of the job. Okay. What can you say about opt? Can you try to, like, what's the relationship between opt and A and P? Which one is bigger? Like compare opt to this. Which one is bigger? Blake?
P.
Okay. P compared to opt.
Well, you said which is bigger, A or P?
Sorry, actually, let's say compare opt to P. Which one is bigger?
Opt is the average.
Opt. Sorry.
Is opt the
No, opt is like
the load spec like
opt is the best maximum load, like the way to minimize the maximum load. So and suppose that you know everything from like you know the whole sequence already. Yeah.
so opt should be greater than or equal to the max job.
You said this should be true. Why is that?
Because if that's the
Anyone?
a machine could have more than one job on it.
A machine could have more than one job. Yeah, but not quite explanation for this actually. Oh, okay. Yeah.
I mean, it's just because someone has to get that job, right? So you can't have a max load of a machine less than P.
Yeah, like just look at the maximum guy. This guy need to go to some machine. So the maximum load need to be at least the maximum guy. Okay, how about compare opt and A? Which one is bigger?
A is bigger.
A is bigger? Like this?
Yes.
I don't think so. Okay, it's like this, but anyone has explanation?
Well, in one case would be that every like the optimal assignment of jobs to machines is like every machine has the same job, and in that case or the same like workload, and then in that case opt and A are the same. But like if you have the case where there's one really big job and one really small job and it's just like two machines, then opt is going to be like the maximum job, but then the average is going to be much lower between those two.
Yeah, so let's see. Yeah, you that's basically right. Let me repeat that. Like let's say that you have like a machine, like 3 machines, and somehow if you can assign like a jobs so that they really just get exactly the same amount of load. In this case, then opt and A will be the same, right? But this is like a really lucky case. In the general case, some of the machine can be like a bit smaller, And if that is the case, then some load of the machine will need to be bigger. Once that happens, then basically the guy that goes up, the machine whose load goes up, will now has load more than the average load. So it's basically asking, this is just basically say that the maximum load need to be at least the average load, which is going to be always the case. Yeah, max is always at least average. Okay. So you have this thing. So that opt is at least both A and P. Okay, so next is we just need to analyze alg, okay, and claim that the algorithm will return something that have cost at most A plus P. Well, if this is the case, then this is at most 2 opt. Right? Because this is at most opt, this is at most opt, so this is at most 2 opt. So this is going to be too competitive. Okay. So how do we analyze this? Well, suppose that T is let's say that Pn is the last job. And let T be the starting time of the last job. What do I mean here? I mean you have this machine, and this is the load so far. Okay. And then the last job Pn come. Let's say Pn is here. Okay. So Pn will be assigned to this guy. And this is T, the time, the starting time of the last job. Okay. And so from here, we know what? We know that one second. Wait. Can this happen? 1 sec, sorry. I was gonna say that alg is gonna be at most T plus Pn. But this is more than this. So good. I want to say this instead. So algorithm, I claim that it's going to be at most A plus Pn. Okay. So, wait.
Wouldn't it have to be A without including the last element?
Yes. Good. Good. Not the last job. Sorry. Forget this thing. So maybe look at this one. Maybe I do it on the board. Oh, the eraser is here. So let's say that like these are the machine, and okay, let's say that this guy has the biggest load. Yeah. This guy has the biggest load. And let's look at the last job of the biggest load guy. Good. Yeah. So let's say this is the last job. Let's say this is like a J star. Okay. So now, so right now we know that algorithm have cost, which is, and let's say this is t. This is like a starting time of the last job of the biggest load machine. So algorithm has cost, which is just t plus pn, pj star. Okay. Now the claim is this. T must be at most A. We can get a bit better than this, like you said, but it's going to be at most A. Why is that the case? Well, like, you know that, like, at the time, well, like, look at the time, like, at the time that that we assign J star to machine, I don't know, machine I, right? Then I has a least load at that point. So you know that, like, it cannot be that, like, T is actually here. This cannot happen because if T actually has, like, is higher than this load here, then like we would have assigned J star to the least load guy.
Yeah.
So T need to be like kind of smaller. Yeah. So I has the least, like, is the least loaded machine. Okay, so the load of I at that point is less than, like, the average load at that point. At that time. Which is less than A, which is like the average load at the end. Right? So the load of I at this point is just T. So we get that T is less than A. Okay. So T is less than A. What about Pj star? Well, at most P. So with this is at most 2 opt. We can get a bit better. claim that we can get something like 2 minus 1 over m here. How would you like do this? Basically, what we are doing here is kind of loose. Okay. So basically, what do I have? Actually, I have that. What do I have here? Like I have that. Right now, let me rewrite this thing a bit. I write that t is less than a, right? Which is the same thing as t times m is less than the total load. Okay. But we actually know that we can say that this sum here shouldn't include pj star. This is the load at this time. So it's the time that we don't have j star yet. So we can actually say that this is less than m times t is less than this sum minus pj star. Is this good? This is a kind of just a bit better. Okay. So what do we have here? We have that t, if I just rewrite this, it's just t at most a minus pj star over m. Okay. So it means that like this is minus pj star over m here. And so this is just like, instead of having, this used to be p, but I can just get a better bound here, which is just write a minus p j star over m plus pj star. So this is basically a plus 1 minus 1 over m p, which is good. So when you think like there are 2 or 3 or 4 machines, this is actually like kind of significantly better. When m is like big, then it's just basically 2. Okay. So we get that the conclusion is that we get 2 minus 1 over m competitive. Okay, good. Right. And I claim that this is tight for this algorithm. This is the best that this algorithm can do. Why? Imagine that there are like, I just decided, like I designed a job like this. There are like m times n m minus 1 jobs of size 1. and then just one job of size m. Okay. What greedy algorithm will do is just to kind of distribute the work evenly first, and then the last job, it has no choice but to put the last job somewhere, right? But if you know there's knowledge from the beginning, if you have knowledge of everything from the beginning, you could have just put the last job to one machine and then put all the other jobs to other machine. And you can see that the competitive ratio is basically 2. To be precise, like a 2 minus 1/m. So this is like the best that a greedy algorithm can do. But there are better algorithms. Okay. But if you want to know what is that, you can look up. But this is just the lower bound for greedy, okay? But actually, I want to say that like we can show a lower bound for any algorithm that work against adaptive adversary. Okay, so I want you to try to think. Actually, do it here in class. Think like you are adaptive adversary. You try to make the algorithm life hard, right? So maybe try to describe how do you force the competitive ratio of any algorithm to be at least 1.5. Okay. And as a hint, let's say that there are just 2 machines, and maybe your sequence will have at most 3 jobs. So maybe spend like 1, 2, 3 minutes to just try to design adaptive adversary. Okay, so go ahead. Okay. Any ideas? David, yeah.
I have an idea, but I don't know if it's 3 halves. So essentially, you first send a job that's only 1, and then you can see wherever it puts it. There's 2 machines. Then you send a job that is 2, and if it puts it on the right, you send
Maybe
a job-
I draw it what you said. Yeah. Two machine,
yeah,
and then the first job is like 1.
yeah,
Okay. And then the second job have size 2.
yeah.
Okay.
So if it puts it on the right, then you send a job of size 3. So no matter what, it's gonna be like the optimal will be 1, but it'll be no matter where it puts it, it'll be greater.
Good. So you have like if it puts here, right? Then you're gonna generate like the last job of size 3,
Yeah,
and now it need to go like the best way is just to go here,
yeah,
right? And then basically like that basically now the cost is like 4, but the optimal cost we know that you could just put like a 3 and 1 and 2 here, so the optimal cost is 3.
yeah,
So very good. Yeah, this gives a lower bound, a valid lower bound of competitive ratio 4/3. So it's like some lower bound, not as big as this yet, but very good. It's actually a lower bound. Can you improve it to 1.5? Okay, Scott.
Yeah, we're allowed to end the sequence like before 3.
Yeah.
Then couldn't you do kind of the same thing, but just with all the same size jobs?
The same size.
So if they're all size 1.
Okay.
Oh wait, no, never mind. That's the one. Sorry.
Right. If they are all size 1, then our cost will be 2, and op is 2 as well.
Yeah. Maybe if it was like 2 size 1 jobs and then a size 2 job.
Okay, 2 size 1. Okay, yeah. So you said that like the first job 1, the second job 1, the last job 2.
Yeah.
Okay.
And if they stack the ones, then you just end it after 2.
If it goes like this, then actually like you just end. And okay. And what if it just go like 1 and 1, then you need to put 2 somewhere. Yeah, exactly. So that's how you design adversary to get this much. So let me repeat this. But I hope you see that like trying to prove lower bound here is basically designing algorithm from the other side. Okay. So just create 2 jobs of size 1, and there are 2 cases. If the algorithm put them at the same machine, in this case, we just end. And in this case, the competitive ratio is at least 2, because the optimal cost is 1, but the cost of this algorithm is 2. But if they go if they put the jobs to different machine, then you create a last job of size 2. Yeah. And then in this case, our cost is gonna be 3, because it's 1 and 1 and 2 here, but op is 2. And you see that this is adaptive adversary, because it try to see where how the algorithm behave and adapt, generate the next one adaptively. Yeah.
So with n machines, do you just create n jobs of size 1 and then always end with like a job of size 2? Or just like to generalize the algorithm as
Good.
it general?
I don't think that will work. Let's see. If there are n machine, and you say that like, what if we just create like a job of size like 1 to n guys? Okay. And good. And then the last job have what size again? I think like the point is that if the last job is really big, then even op will need to be like as big as this thing anyway. So that's what your idea, right? Like, so in this case,
I was asking if you could still just do last job size 2.
last job size 2, that would work too. Yeah. So yeah, like basically you can good. You can get this lower bound for any number of machines. Just create n job of size 1 and the last job of size 2. Yeah. Good. Everyone with me here? Like this works for any number of machines. Okay. So now what's the state of the art? So what you just have seen is like super long time ago, 66. But actually you can do strictly better than 2 for any number of machine. This is the best known. It's still quite a long time ago. But the lower bound side is also like not too good. Like this is what we see is 1.5. That works for deterministic algorithm. You can get this lower bound too, better than 1.5. And you see, this is like super fundamental problem, really like a natural problem, but the gap is still there, and like. I really think like it's some good problem to look at. Yeah, try to close this gap is a good one. Yeah. And the only thing you need to do is like maybe just look at the survey of skull, and just to be more precise, this is like a state of the art. So you see greedy when the number of machines increase. It's basically 2, like competitive, but there are better upper bound here, better than 2, and better lower bound for deterministic algorithm is this, like not 1.5, but something better, but it's not close yet. Okay. So like it's basically close only here. And what about randomize? Randomize the lower bound that like there is a lower bound that works is even against oblivious adversary randomize, which is better than 1.5 that we have seen. Okay. And and the upper bound here is kind of not known. Yeah, like it's as good as this one. So yeah, how to get the right answer here, I think is a good question. Okay. All right, so that's it for today actually. So next class we're gonna do like you see primal dual algorithm from last class. we're gonna use it again in the online setting. Yeah. We're gonna see the optimal algorithm for ski rental and like a online version of set cover. Okay, yeah, that's it for now. Yeah, see you next time.